Yeah, everyone, welcome to another video. Today we're going to sort of talk about probability density functions, and this is one of those topics that everyone knows how to use probability density functions. No problems, like they all understand it, but very rarely see anyone that sort of understands like where they come from or like, why they work. And it is actually very difficult concept to understand where they come from and how they work. So I'm going to do my best today. Feeling a bit crook, but to sort of explain sort of where it comes from. So up until now, we've sort of been sort of talking about discrete random variables where we have sort of different categories, like, x could be equal to 1, x could be equal to 2, etc. So they're discrete because they're sort of different categories. Now we're talking about continuous random variables. So random variable that could be equal to anything, and usually that comes from measurement. Okay, so measuring something, so time or weight or height, things like that. How many hours you spend studying per week, as you see on the screen. So we look at those things and they're continuous. So the value could be equal to anything. And if you've studied other statistics, you know that sort of when we've got continuous variables, then there's an infinite number of possible answers there. And so we can't just put them into a neat little table and say how many times each one happened. And so what we do instead is we make a histogram of those. And so we sort of look at like, well, so in this example here that I'm about to go through, the number of hours studied per week. So if you're a student and I go and ask a million students, well, in this case, 100 students, how many hours do you study per week? Some of them might be, say, 10 minutes. Some of them might say 45 minutes. Some of them might say, three and a half hours per week, whatever. And then we put it into a table and we say frequency. How many times did a student say that? So that's called a what's that called? I can't remember what that's called. Frequency table. That's what it's called. Lost me there. So we can put it into a frequency table like that. Then we can put it into a histogram. So, and what it means is that how many times did students say between 0 and 1? They said 10 times. So we do our little histogram there. How many times did students say between 1 and 2? 30. So we draw our histogram like that. Sorry, it's a bit rough, very rough. 2 to 3 was 40 students said between 2 and 3, and 20 students said between 3 and 4. And so there's our histogram, right? We've got frequency on the vertical axis and hours on the x-axis there. Um, and so with that histogram, that doesn't tell us anything about probabilities, does it? But we could actually do something to make it about probabilities. Okay, so if that's frequency, and let's just look at this one here, right? Let's look at that column there. That's telling us that 30 students fell in between 1 and 2 hours for the number of hours that they studied, right? And so we could divide that by the number of students that we surveyed, and we could change that into a relative frequency. So if we come down to this next graph just down here, so you just have to humor me sort of doing this, but if we have the relative frequency, and if you remember from probability studies, probability when you do experimental probability or whatever, and you say, well, the experimental probability, if I interview 100 students and 30 of them say that they study between 1 and 2 hours, that means that there's 30 divided by 100, which is equal to 0.3. That's I guess, the probability that a student will say between 1 and 2. So it gives us a probability, an experimental probability. And so we can redraw this graph between, so between 1 and 2, we had 30 students, so 30 out of 100 is 0.3. And you'll see the graph is exactly the same, but we've just changed the axis, okay? So, and it was 40 students, so 0.4 between there and there. Sorry, my wobbly arm, look at that. Getting old and wobbly. And so we have this histogram. And so now the histogram is not with frequency, so it's really not a histogram then, is it? It's relative frequency, that relative frequency is really just what the probability is, okay? So the probability is there. And so once again, if I look at one of these columns, that column there, that's saying if I ask a random student in the school, there's a 0.4 chance or a 40% chance that they'll say between 2 and 3 hours. So that's what that means. Okay, now I'm just going to go through a couple of things. To start, what we're going to start doing is looking at this and start thinking about it as the area under the curve. Because the question is that students ask is, How is the area under the curve equal to the probability between two values? And it's very, yeah, it's a tricky one, and a lot of people sort of avoid the topic when you ask them. So let's just have a look at this, right? So let's have a look at the area. Just find this black. The area. Let's go probability. All right, probability between 1 and 3. Let's say x. So let's say that x is the number of hours studied per week. And let's say if we're trying to find the probability that a student says between 1 and 3 hours. In other words, we're sort of looking at this, that there, and that there. Okay, probability. You go, well, that's easy. If I want to say what's the probability between 1 and 3, that will be equal to that first probability. So the probability in, I shouldn't really scribble, I'll say area A. Okay, so it's equal to the area of A plus the area of B. Okay, so, well, I'm not saying area A, area B, but 0.3 plus 0.4. I add those two probabilities together and I get 0.7. That's easy. And of course it is. There were 70 students that said between 1 and 3. And so 70 out of 100 is 0.7. It makes sense. How does this link to the area? Well, let's just have a look at the areas of these two. So let's have a look at area A. I'm going to be a bit squeezy here. But the area A, what's the area of that rectangle there? Well, it's 0.3 times 1. And the area B is 0.4 times 1. And so that's equal to 0.3, and that's equal to 0.4. And so if I add those areas together, I'll get the probability, right? Okay, so that's good. Wow, that's nice. And so let me say this, but I'm not finished yet. But if I add the areas under the curve, in other words, between 1 and 3, if I add those areas together, then I will get the probability. But let me just check something. Let me just check the total area under here. So the area of that one is 0.1. The area of that one is 0.3. The area of that one is 0.4. And the area of that one is 0.2. And if I add all those together, I get 1. Okay? And that's what we want. We want the probability of all the possible things happen to equal 1. That's probability. That's life. We need if we add up all the probability of all the possible things happening, it should equal 1. Okay, so that's just what I want you to remember, because what we're going to do now is go, well, what happens if we want to make this histogram here? Let's make it smaller, right? So in other words, by smaller, I mean, let's break up those gaps between 1 and 2. Let's make it a half gap, so 0.5 gap, and see what happens, right? Now, I'm just going to make up some numbers, so bear with me, right? So before we had 10 students. So I'm going to come to this graph. I'm going to come down here now, okay? So let's say we had 10 students, and let's say 4 of them were between 0 and half, so between 0 minutes and half an hour. And so what that means is I'm saying 4, let me just write it on here. So let's say 4 were between 0 and 0.5, and 6 were, let's say adding up to 10. And so 4 divided by 100 will be 0.04, right? So that will be, I'm just making up numbers. Let's say 0. Oh, I've messed that up. So let's say that between 0 and 0.5, let's say that will be 0.04. So 4 out of 100 students were between 0 and half an hour. And let's say 0.06. Sorry, my sketching is not great and it's not very accurate, but you'll forgive me. 0.06, those things add up to 0.1, so that's okay. Adding up to that there. So what I'm doing is I'm going back to my original data, if you like, and I'm going, oh, those guys, had 10 students, say, between 0 and 1. If I go back and say, let's break it up into smaller chunks and go, oh, actually, 4 of them said between 0 and 30 minutes, and 6 of them said between 30 minutes and 60 minutes. And so I'm just refining my little histogram a little bit more. Well, let's say for those 30 students that said between 1 and 2 hours, let's say that 10 of them said, so 0.1, 10 of them said between 1 hour and 1.5 hours. And that one's going to get in the way of my next line. And that would mean what do I need? I've got 20 of them will say between 1.5 and 2 hours. Okay. Sorry, I probably should have drawn it a little bit bigger. Okay, so 0.2, and that one there is 0.1. Okay, they still still see that 0.1 plus 0.2 still adds up to that 0.3, that 30, and that there. Okay, so all I'm doing is just making up some numbers and showing you about what happens if we go in a bit further. Okay, so 40 students. Let's just say it was let's say 40 students. Let's say I don't know what 25 of them. 25 of them. So 0.25, set between 2 hours and 2.5 hours. So that would be 0.25. And let's say that would leave 15 students that said between 2.5 and 3 hours. So 0.15. I've got such shaky hands. Don't get old. It's bad. And so we've got that. And let's say those 20 students remaining, let's say there was 10 students that said 3.5. And another 10 students that had 3.5 to 4. Okay, so it'll be 0.1, 0.1. All right, let's have a stare at this for a second. Okay, so what I've done is just made up some numbers and we've had a look at this. I've made the intervals for each bin, for each histogram bin. I've halved them. Okay, and we're getting this, and we're sort of getting more of a shape to the curve. It's becoming more of a curve. Now let's have a look at this. We said before that the probability of x between 1 and 3. It won't have changed because nothing has changed here. It should still be that plus that plus that plus that. Okay? It won't have changed, and so that still should be 0.1 plus 0.2 plus 0.25 plus 0.15. That should still add up to 0.7, 0.3. Yep. So that still adds up to 0.7, right? Nothing's changed. I haven't changed the data. I just sort of, broke it up into little pieces, right? But how does it relate to the area? So let's have a think about the area. So go to area again. Let's find the area under this curve, if you like, the area of those rectangles, okay? So the area under the curve is equal to 0.1. So I'm looking at that first one. So let's just call them A, B, C, and D. A is equal to, that's a terrible zone. I should just use my eraser instead of wasting everyone's time. Area is 0.1 times by the width, which is 0.5. B is equal to, what is that? 0.2 times 0.5. C is equal to 0.25 times 0.5. And D is equal to 0.15 times 0.5. Okay, so there's all my new areas there. Now, what I'm going to do is if I add all those probabilities up together, okay, so then so I'm going to go A plus B plus C plus D. If I add all those up, then what I'm going to get is I'm going to get 0.5. If I take out 0.5 as a factor out the front, I'm just going to get 0.1 plus 0.25 plus 0.2 plus 0.15 again, okay, you're familiar with that. So that will be the total area there, okay. Now, you'll notice that this is half of this, right? It's now half of that area before that we did. And so that's not right. So that probability is not equal to that. So now all of a sudden the area under this curve is not equal to the right thing. It's been halved. And I've actually halved the bin width and I've halved the area here as well. And so what we do is what we look at this is go, well, how that should be, if we want it to be the area under the curve, then what we need is we need to actually make sure that the total area under the curve is equal to 1, right? And so what you look at this is like if I actually do this, if I divide by 0.5 here, that'll cancel out there, and you'll get what you should get. And why did I divide by 0.5? Let's have a look at the total under the graph, right? And again, this is hard to describe, so I hope you're sort of following, but I understand if you don't, right? So if I add up everything under the graph, 0.04 plus 0.06 plus 0. If I add up all the areas that I've sort of got written here, if I add up all the areas, the total area, you have to just trust me on this one, I get 0.5. And if I divide the area, that yellow area, divide by the total area, that will be my probability. And that's actually what I've done here, okay? If I add up all the yellow area, that's the yellow area, and if I divide it by the yellow plus that blue area, so the total area under the graph, so that's the total area, that should be yellow plus blue, sort of, yellow plus blue on the bottom line, then that will be the probability of A, B, C, D happening, the probability that X is between 1 and 3. I hope you can see that, right? And so the next logic jump is the last logic jump that you need to make. And so what that means is that if I keep doing that, right, if I then halve the bin width again, then what happens is that the area will halve, and then what I divide by will be, whoops, I'm still on. So what the next line, if I halve it again, then the bin width will be 0.25. I'll still have all the same things, 0.25 plus 0.2 plus 0.15, and divided by, and the total will be, you have to trust me in this, but you can practice it. If I divide by the total area, then it's going to be equal to the original thing, which is what we want, so the 0.7. So what does that mean? It means that if we want to put a line on this graph, and call that the probability density function, then the area under that curve will give us the probability between two values, right? Only if the area is equal to 1, right? Only if the area is equal to 1. In other words, we need to divide by the total area. And so what that means is that when we talk about a probability density function, what it is, it's actually been scaled upwards, okay? So here, we said for this graph here, for that one there, we said that the area under the graph, the total area in the graph was 0.5. So that is not a probability density function. What we need to do is scale it. We need to double the height of it to make it into a probability density function. We need a total area under the curve of exactly 1. And if it is, then that line that's generated, that nice curve as those bin widths get smaller and smaller and smaller and smaller, and the curve becomes a perfect continuous curve, then the area and then the area under the curve will be exactly equal to the probability between two values. Now, I hope that makes sense. It's very hard to describe. If it doesn't make sense, I'm apologies, but it's hard to describe to people. But hopefully it gives you a little bit of an idea that we start with a histogram, we break it up into relative frequencies, which are your probabilities, and what we do is we scale the vertical scale here. We change that scale of the probabilities so that we get an area of 1 exactly under the curve. That gives you your function, and that's called a probability density function. And then we can use that for all sorts of things to be able to find the probabilities between two values, between, let's say, 1 and 3, or between 1 and 4, etc., etc. I hope that makes a bit of sense. It's a difficult concept to teach and to learn, but we'll be using this fact in coming videos. Thanks very much.